The first question is like for example, every day we have a process that looks at a large collection of LLMs, pretty much all of the standard LLMs, and we are assessing how well does it do in generating Wolfram language code. We have a nice table. Actually, we're about to start publishing these tables. It's kind of interesting, actually. So there are two levels. First, is it syntactically correct? Second, does it, so what we did was I wrote a book some years ago, Introduction to Wolfram Language, which has exercises. And the exercises have an English language description, and then now you're supposed to write code. We have a pretty good and now tested, gazillions of times, testing system that says, is the code that got produced, that got written by the student, so to speak, quotes, correct code? Okay, so we have good test for that. So now we ask, for these LLMs, do they produce syntactically correct code? Do they produce essentially semantically correct code in the sense that it does the thing that was supposed to be done? So you could just look at those numbers. I mean, there are, they get different percentages of success. But I think, to this question about does it parse, does it turn into Wolfram language code? That's a lower bar than you need, because it could turn into code, but the code just does something totally crazy. The question is, when you ask the question, does the code do what the code should have done? The code does not in and of itself, the code will just do what it does. It is the description of what it should do, is that code. So to ask from the outside, did it do what it was supposed to do, is a different question. And you could, for example, you could say, if I take random cellular automata, and if my code defines a random cellular automaton, and I run it, and then I say, did that do what it was supposed to do? Well, that's not in and of itself a meaningful question, because it did what it was, it did what the code said it should do. And now the issue is, well, was it the thing we wanted it to do? It reminds me, in the world, a very different world, in the world of cryptocurrencies, there was this situation that you're probably aware of, this DAO thing that happened, I don't know, 8 years ago or something now, on Ethereum. Somebody set up this thing. There was a thing, the Distributed Autonomous Organization, and its big banner was, this thing doesn't have humans in the loop. It just operates according to code. And it just, its laws are code. And then somebody transferred $50 million to their account. And people said, but you can't do that. And the person said, but I just followed the code. But people then said, but you're not supposed to do that. But this thing was defined by its code, so to speak. So it's kind of I think this question of, did it do what you wanted it to do, is a complicated question. And in the end, what it wanted, in the end, it becomes almost it's very analogous to sort of an ethics question. Did it do the thing that you thought it should have done? And that becomes this huge network of, how does it connect to every part of, in the case of mathematics, good example of this, okay? Ramanujan, famous mathematician of the early part of the 20th century, discovered this result. E to the pi square root of 163, I think, is very close to an integer, okay? To most people, that would have been a random fact of mathematics, of no significance whatsoever. In fact, I've even gotten postcards from people with similar near integer statements, which I don't think have any significance. But to Ramanujan, that thing became something of great significance. That became actually one of the standard ways to compute pi, among other things, and a bunch of other number theory. So this question of what took it from the random fact to this thing that is, quotes, interesting, is interesting to consider, because it was basically, I suppose in that case, it was the success of building kind of a tower on top of that result, I suppose. But I think that's for language, I'd be curious whether, is there a rating? If you said, I've got these sentences, and, one of them is from the Jabberwocky poem, and another one is from whatever else. Is there some sense? Can one imagine a rating of, what is it? Is it interestingness? Perhaps it isn't interestingness. Perhaps it's, what is the thing that goes from, I don't know, happy electrons, it's hard to make a nonsense sentence. Happy electrons kind of eat turtles or something. Um, the that appears to be a nonsense sentence without further context. What's the? I mean, okay, in this project that we're doing, the symbolic discourse language project that we're doing, we will have a very precise sense in which sentences are meaningful or not, because they're basically being turned into something that is computational.
Well,
Yeah, kind of following up on that, I was curious about the semantic grammar point that you mentioned and this kind of question about what is it that linguists may have missed and that language models seem to have picked up on. So I
Uh-huh.
think I would have thought of it as kind of the success of the distributional hypothesis. So going back to Paris and like Firth and this idea that, you shall know a word by the company that it keeps, that idea with language models seems to have turned out to be much more successful than I think people initially thought or predicted. So things like Adele Goldberg, the construction grammarian, has all these nice examples of to know the meaning of a word like red. You need to know that, a red grapefruit is red on the inside, but a red apple is red on the outside. And red square isn't really red at all. And red hair is not really red either, but we kind of just call it red. So is that that to me feels like the kind of knowledge that you're getting just from language usage and keeping track of these statistics? And it's the kind of thing language models seem good at. Is that part of what you would mean by the semantic grammar, or is that something
I mean
else?
something more precise. I mean, that's an interesting thing in its own right. But, if you imagine, so for example, logic is an abstraction of language that tells you about sentences that make sense. In other words, I could make a sentence, think syllogistic logic, for example. I could make a sentence, all men are mortal, Socrates is a man, therefore Socrates is a turtle. Right? That doesn't, that isn't a logic. I could have a better version of that. So logic is a kind of an overlay on language that tells you which sentences, potentially make sense versus which sentences just are syntactically correct, but aren't saying something that's true or right or whatever else. So my point is that I think there are a huge number of other kinds of constructions, and there are pieces of I don't I try to do my homework, but I certainly wouldn't claim to know every corner of the world of linguistics. But there are things, whether it's frames for verbs and things like this, where people have tried to sort of make the beginnings of a construction kit for what goes with what. But if you say, here's a motion word, and you say, and here are place words, just like we can say here are nouns and verbs and so on, we could say, a place verb, you go place word, motion word, place word. That's a thing that can make sense. But, place word, motion word, emotion word is probably not going to make sense, or some other. So that's the kind of thing I mean. And I'd be curious. I mean, there have been various attempts, I think, in linguistic history to sort of set things like this up. And, some of them have been very, there was the semantic primes effort uh, that was from the 1960s, I guess, that kind of got mired in, which I thought was an interesting effort. I mean, there was also efforts in constructed languages, of which my kind of two favorite examples, which are the two extremes, are Ithquil and Tokipona. Ithquil being the
Yeah, yeah.
maximal constructed language and Tokipona being a minimal one. I was very sad to realize with Tokipona that if you didn't use languages like Finnish as the word roots and used English instead, it sounds like baby talk, which is sort
Yeah.
of interesting. And it's not totally surprising because it's
Yeah.
got very simple, structure. And it's like, and you're saying things like, you know, food want now. I don't know what, you're simplifying the structure, and it sounds a lot better if you use its weird, its actual weird morphology and so on.
Hello.
Yeah, it's interesting that it feels to me like there've been a lot of these efforts, well, as you're saying, over the years to translate natural language into these kinds of representations. And it turns out to be really hard, in part because so much of what we say ends up not having these kinds of logical forms, and or even words that seem logical, like or and turn out in practice, or sometimes is logical, or sometimes it's very different, or like will is kind of like, at future time
Sure.
T5, but a lot of the time it's more like a prediction or an assertion or different kinds of things. And so this kind of relating to what Roni and I were talking about in our session earlier is that kind of one of the things that I take away from the successive language models was the idea that, well, maybe if you can just avoid having to do that, like the actual bit of processing language gets easier because you get these fuzzy representations without having to turn them into these kinds of things. But then at the
But I
same
think
time, you run into this problem that then how do you turn them into parsers to do, Wolfram Alpha?
yeah, right. It
Yeah.
depends what your goal is, right? I mean, one one point about sort of the failures of the philosophical languages, as they were called in the 1600s, you know, my main conclusion about this is just because people haven't succeeded in doing it doesn't mean it's that hard. I mean, and like for Wolfram Alpha, for example, we were building a general question answering system, and there was 50 years of failures in doing that. And so the question is, why were we able to succeed even given all those failures? And I only realized in retrospect what the answer to that question is, other than, just having engineering capabilities and all that kind of thing. The real answer was because we had this computational language that we could hang things on, we were not trying to do abstract natural language understanding. And we were not trying to do, we were trying to actually take something where we had a target. And by the way, an important point about that in the symbolic discourse language effort that we're doing. So here's the point. People are working on this. I keep on telling them, forget the words in English and and the particular meanings they happen to have, like the word red, for example. Um, you know, there is take what we've done in Wolfram language, for example. We have the word plus. The word plus in our language has a very definite meaning. It means you're adding things together that are a bit like numbers, and it has all these properties that x plus y is y plus x, all these kinds of things. We've hijacked the English word plus, and we're using it for our precise meaning of a plus thing. It's useful to have that English word because when people are reading our language, it gives them some kind of cognitive hook. It isn't just, function 752, which they'd never understand what it was. But then we're taking that word, we're hijacking it, and we're turning it into some very precise computational thing. So kind of what we're trying to do in this symbolic discourse language is to do that same kind of thing across other domains of understanding of taking, and we've done this now for a huge number of domains. And the things we haven't done. So typical example, I want to eat a peach, which I was going to do actually. The we have a lovely representation in Wolfram language of a peach. We know its species, we know its nutrition content, we know lots of things about the peach. We don't have a representation of I want to eat. And so the challenge is to have a representation of those kinds of everyday concepts. Now, one thing we'll do in turning things into the symbolic discourse language, if there was any poetry in what you said, it will be crushed out because it's going to be just, this is the raw computational compatible meaning. And I think let's be clear, this is not, quote, solving the problem of language. This is making something that is an engineering technological solution, which seems to have a bunch of applications. It allows you, let's say you write a contract. You can write a contract in computational language then, and that contract is automatically executable and so on. And that's potentially useful, but it isn't solving the problem of answering, the question of, for example, how do humans generate language? That's a different question. And I think but the fact is, my impression, my guess is that there's this framework that is this kind of semantic grammar framework that neural nets have with huge effort. They've kind of adapted themselves to this. I mean, one of the other lessons of neural nets is, which people are learning now, is it takes a lot of effort to train it. But once you've trained it, you can start, instead of using a precise real number weight, you can reduce it to a 2-bit weight or something, and the thing will probably still work. It takes a lot of effort to navigate through to this trained state. But once you're there, you can strip away a lot of kinds of things. I mean, I think it's yeah. Seems like Ava has something to say here.
Go ahead. Yeah, no, I was just going to comment on the fact that LLMs, one of the big differences that they have compared to models just from a couple years ago is that they're trained on large amounts of code. And you made the interesting point that when we write code, for it to be more human readable, we do tend to sort of name things with names that are similar to natural language in some way, even though they may be defined as like specific functions and therefore have very, very clear, definite definitions. And I wonder whether or not the fact that we have now trained these LLMs on so much code and that at least correlates with them doing much better, whether or not there may be a relationship there, if the fact that they have been suddenly trained on all of this defined and sometimes even grounded in the form of assertions and code has somehow helped them then generalize to like their usages in natural language as well.
Here's my guess. People were really surprised that LLMs could do logic. My statement was LLMs learned logic the same way Aristotle did. That is, imagine you were inventing logic from nothing. You would say, I'm going to look at all these sentences. I'm going to see the ones that seem to make sense. Then I'm going to abstract from those. What's the structure of the ones that make sense? And I think that's what the LLM did too. I mean, the LLM is very poor at, when you have a tower of things that you have to figure out, it's pretty poor at following that tower. It's not what it's good at. It's good at, you ask it to do parenthesis matching, it will fail after a certain number of parentheses. And the deeper the longer the look back in the transformer and the deeper the stack and so on, you can get it to go a bit further. But fundamentally, it's going to fail at a task like that. But yeah, no, I think it's an interesting question. I mean, one thing we've been interested in is, Wolfram language is the unique example of a language where it is a computational language that is intended, well, first of all, that attempts to actually represent a large chunk of the world, not just the particulars of how a computer works inside. And point one. And point two, it was built from the beginning to be a language that could be read by humans as well as written by humans. And so it's a sort of special case. But we've been pretty interested in whether there is transferability from, it read a lot of C++ code. Does that help it in writing Wolfram language code? We don't know the answer. I mean, we know that, an interesting thing is it writes pretty good Wolfram language code, which I find interesting because there's plenty of examples of bad Wolfram language code out there. And also the obvious translations from procedural programming languages, for example, would lead to bad code. But typically LLMs don't write bad code. They typically write pretty nice, compact, functional code. So, I mean, that's but it's an interesting hypothesis that by seeing sort of the structure of code, that it's kind of like a version of seeing something like syllogistic logic, of seeing these are things that fit together. I mean, look, one thing, okay, it's been a long time question of mine. Okay, have to ask it with linguists and so on. I want to get a spoken version of Wolfram language, and I can't figure out how to do it. Even though it is a tree-structured language, it's context-free language, it has the same, you can look at its parse trees, they look just like human language, except they're more structured. But yet, humans have a really hard, I just don't know how to do it. I think there are probably markers and, it will be a lovely thing to solve because there are a bunch of use cases, particularly in education, where you really want to be able to speak that code, but you want to be able to speak it in a way that people can do transcription trivially, so to speak. It's sort of that maybe speaks to this question of transferability of, because, regular natural language is speakable, one assumes. But yet, well, code generically has not been speakable at all. Wolfram language code has the best chance to be speakable because it has actual words in it and things that you can use as kind of cognitive hooks. But I just don't know how to do, f of, I can say f of x, right? You understand that. That's easy enough. F of g of x, comma, h of whatever, it loses it very quickly. But I'm sure there's got to be a way of having, just like in natural language, there are all these tricks for, these markers of where you go in a sentence. There's got to be a way to do that. There's got to be a way of filling in fluff that represents those commas and things like that.
Let me address the question to Caillou. Okay, you go in auto formalization. You go from English to formal code. what Stephen is talking about is going from formal code back to something like English. Is that
not really? Not really. That's not what I'm talking about. I mean, that's
Wolfram language.
That's a different problem. Wolfram Alpha is going from natural language to formalized language. Just like, I mean, it's the same problem, but a different use case from the quotes auto formalization. I mean, there's a different question, which is, given a piece of code, have the LLM write a description of what that code does, which it's reasonably good at. Although, people say, well, then that's a way to understand the code. But the truth is, if you have a well-designed computational language, the code is probably the best way to understand the code. But I'm curious, do you, I mean, if you say, I mean, actually, so there's another case we've certainly looked at extensively, is explain the proof, basically. So we have in Wolfram Alpha, we have the show steps feature, which happens to be super popular among students and things. Although we've never done the kind of educational piece of terrorism of randomizing the steps. We've always had it be the case that, if you're a teacher, you can actually tell it's a Wolfram Alpha generated show steps. LLMs do randomize the steps, although they often get the steps totally wrong. But that's a case where, we've been interested in how do you take this computation and break it down for human explainability. And there've been lots of people, I don't know, do you work at Meta? That where you work? Yeah. There are people there who are interested in maybe it's even your group, I don't know. But I think who've been I mean, a bunch of people have been using our tech to kind of explore these kinds of questions.
I think what I've been doing is try to give the language model a formal proof and ask it to explain it step by step. I think mostly it, I mean, maybe I would say maybe 50 or 60% of the case, it explains the step fairly well, but still, it often gets a high level picture right, but for a specific term in the proof, a specific operation, I feel it's not that accurate. And I feel like I guess maybe it's similar that this problem also exists when you talk about how to get a spoken Wolfram language. I feel like the programs are very compositional. You have all these parentheses, you have terms, compose them together, you have a very deep tree. Although natural languages such as English can also be compositional, you can have clauses, but usually they are never compositional to that level. At least in the language we commonly speak. So I'm wondering what's your thought on I mean, if you want to really do a spoken programming language, how do you deal with this?
Well, I think that's why you define subfunctions, so to speak. That's why you define little functions and you put the little functions together. I mean, once and typically that little function is going to say, you're going to have a name for that function. Just like if you're saying, I will call this, a plig, and then I'll go and talk about that. I mean, I think, it's interesting to see there are things like pronouns, for example, which exist in natural language. We have a direct analog of that in Wolfram language. We have in anonymous function, in pure functions, we have these hash signs that represent a thing that can get put into that slot. And so, for example, in natural language, we have some tricks with pronouns like gender and number and so on, which allow one to sort of multiply. Instead of just saying it's a this, you say it's a he, it's a she, it's an it, it's a plural, it's a they, et cetera, et cetera, et cetera. And so, it's interesting to try and see to what extent one can, I mean, there are structures like that we don't quite have complete analogs for in computational language, but it's sort of interesting the extent to which those are used as tricks for helping us more compactly understand natural language in a heuristic way. Because if you say, I don't know, the cat chased the dog and it ran fast or something, you don't know what that it refers to. If you say, Oliver chased the cat and he ran fast, then assuming we're in a gendered world where Oliver is a he, we kind of know what that refers to.
Well,
I'm curious. Go ahead.
That's pretty garden variety question about anaphora and the way that it gets solved in language. I'm wondering about another aspect for Wolfram language. Prosody was created or evolved in order to handle spoken versions of things that, if they were simply written down without punctuation, wouldn't be understandable in English either. Can turning Wolfram language into spoken form make use of prosodic tricks?
Yeah, it's an interesting question. There was an issue like this a number of years ago in Wolfram Alpha. When it's used in intelligent assistance, it would often generate, we generate a table of data, like, this is the population of this place, this is the population of this place, blah, blah, blah. If you read that table just straight, it's hard to follow and really boring. So I had this idea of, what if you sang the table, so to speak? Or what if you had kind of musical indicators in the table, and you made, funny beeps and things at different times. We did some experiments. It never really caught on, but I think that's an interesting, as a way to, at least on the output side, I have thought about that, of to what extent you can, actually, we even did that. We did that in some generated spoken results. Yeah, and in fact, that was even deployed in one of the intelligent assistants, maybe Siri, I'm not sure, we actually had some, the problem was whether we could control the final deployment of the voice well enough by marking up what the results were. But yeah, no, it's an interesting question, and I don't know. I mean, one isn't used to in the translation to prosody from written language. I mean, I don't know. You can presumably have little scan marks on top of the text, but it's not. It's kind of a meta layer of human presentation of those things, I think.
Carl, can you think out loud for a few seconds so we know how this is striking you? You haven't said anything.
Thinking out loud. I'm tempted to say I'm a good large language model. I only speak when spoken to. So thank you for speaking to me. I'm thinking again about cross-cutting themes. I'm coming back to something that was recurrent in Stephen's talk, which is finding those things that we care about. And I think that theme re-emerged in discussion. Again, Stephen asking the question, how would we know that this is sensible? Does it make sense to me? And how would you quantify that? And how would you formalize that if you wanted to? And it strikes me that's a really important question, and not only important, but very prescient for language, and indeed relevant to the extraordinary coupling and synchrony we see between users and large language models. So I was just wondering how I would answer that, and put it forward as a suggestion and invite comments upon it. It seems to me that there has to be some, again, coming back to a lot of the content or the discussion of the Ruliad, there has to be a relational and observational aspect to how you score how much this thing makes sense to me. And specifically, this thing is something like me. I share some frame of reference, some common ground with this thing that's generating something that may or may not make sense to me. It strikes me one very heuristic way of looking at that is that if this sentence or if this code or if this message affords a solution of the hermeneutics problem, then that will be one way of scoring whether it makes sense to me. And by the hermeneutics problem, I simply mean, can I infer what is meant by that message, that language, that sentence, that piece of code. And I'm just wondering whether one could articulate that in terms of the information gain and the degree to which it resolves uncertainty in me about you. So to put that sort of interactivity in a game. So I'm just putting this out there, you know, and I'm sure that that question could be answered from a number of different perspectives. But is there any way of being able to quantify and formalize the exchange of information between two things that rests upon a common commitment that may underwrite the exchange of information?
I can give you a criterion. I'm not sure it's a very good one. Imagine you're doing mathematics and you're, you know, and one side is saying, here are some theorems that are true. And the other side is saying, well, what can I conclude from that? You could say that before you have those theorems, two things are not, you know, you don't know whether they're the same or not. As soon as you, as soon as you get one of those theorems that shows equivalence, you've just connected those two pieces. So one criterion you could imagine is you've got a stream of, you know, one interlocutor, so to speak, is speaking a stream of theorems. And you can ask the question, to what extent does that, how much, you know, previously to the other, you know, to the other party, there were just a bunch of scattered theorems all over the place. They didn't connect together. But suddenly they're told a connection, and then they start to join up. So you could imagine a situation where you could say, you could ask the question, given the stream of things that are said, how much joining up is going to happen? I mean, that would be an example of a criterion, you know, a little bit of a meaning-based criterion for what did you learn, so to speak. I mean, it's you know, the joining up of theorems, the knowing what's equivalent to what might not be sort of the whole story, but it's, I mean, you could imagine another thing. You could imagine, I mean, you could imagine any kind of system like a Boolean expression with many variables. And, you know, person A suddenly says, you know, P7 is true. And then that reduces the, you know, then the set of expressions that, you know, that then you have a simpler expression. I don't know. I'm trying to think, what else could you do in terms of understanding what, you know, it, in a sense, what you're saying, the reduction of uncertainty is taking what were arbitrary values and instancing them. Like for Boolean expressions, it might be, you know, P could be either true or false, but now we know it's true. And I suppose that, yeah, I mean, what one could just imagine yeah, I mean, even in that case, one could just imagine a space of possibilities. There are n variables, there's 2 to the n possibilities. We start supplying values of variables that will reduce the size of that space. You know, it isn't 2 to the n anymore, it's 2 to the n minus q or something. I'm not sure how, yeah.
Well, no, I mean that fits very comfortably with the sort of information theoretic treatment. So it's like that winnowing down, you know, namely finding those that sort of coarse-grained structure, and which you could now indeed start to relate back to Komarov complexity and the like, or you could just articulate in terms of, you know, good old-fashioned information theory that you're reducing the entropy. You're maximizing information gain by reducing the entropy from a probabilistic point of view. That would be one way you could articulate it.
Although I think that, you know, in normal sort of Shannon information type stuff, the typical use case there is just, you know, block compression, so to speak. You're not asking sort of how did the program, you know, what could you run from a program? You're just asking, you know, after every Q, there's typically a U type thing. You can say there's compression at the level of you know, picking only particular blocks out of all the possibilities. So I suppose the analogous thing would be the statement that, you know, if entity A says, by the way, after every Q, there's always a U, that will immediately reduce the, you know, the number of possible possible sequences of characters that one might have to consider.
Kyle.
Yeah, I was just going to mention that I think there's a relevant in the linguistics and cognitive science literature, some relevant work thinking about the way that like semantic systems of particular spaces, so things like color words, can be like you can use an information bottleneck approach to look at the way that the kind of space of words used to describe a color grid can be thought of as exactly trying to maximize the informativity while minimize the complexity. And so there's languages that have only 2 or 3 color words, which is great and efficient, and you don't have to learn as many words, but you're right, it comes at this cost. And there's a paper I was involved with, and there's been a bunch of literature on this, that you can actually, in information theoretic terms, quantify for a given color system, how is the informativity of the space of color words about the same color grid across languages trading off, and you get these kind of nice curves showing that languages which have more complexity in the system use it kind of optimally to maximize the amount of information being conveyed. So that's been done in like
I'm curious about that. So if we take a color space, and obviously the perceptual color space for us is like XYZ color space or something. It's not RGB. So we take our perceptual color space based on our photoreceptors, and then we start saying, okay, this is red, and that's some region in color space that represents that. So one question would be, and it relates also to what one cares about, because one might say these 2 shades of red are, pink versus red is profoundly and distinctly different. And so we really care about making a distinction between these. Or you might say, like in ancient times, green and blue, I don't know, in ancient Greek, people say green and blue didn't have separate words. How did I'm really curious, actually, how did, so presumably you can ask native speakers of these languages what they consider these, what word they use to describe these colors.
Yep.
And when you say there's optimality in what went on, what do you mean by that?
So optimality across languages. So the experiment is basically exactly that. You show people a color grid. It's called the Munsell grid, which the colors are perceptually equally distinct in space.
That's a particular, I mean, it's a well-used, it's like Pantone colors and things. It's a well-used sort of graphic design color space. I'm not sure that it has physiological basis. I mean, it has Western graphic designer basis.
Or perceptual. I think it's based on, I don't know if it's physiological. It's supposedly based on perceptual experiments.
By Western graphic designers.
Yeah, possibly.
Definitely. I mean, that's, I'm just making that point. It's a, I know your job is hard. Your experiments are difficult to do. I'm just adding an additional piece of complexity to it.
It's not just designer artifact, and it's not the Berlin and K international color chart comparison showed that for all cultures, even if you look at the chromatic spectrum indifferently, some parts of it produce a bigger difference. The rainbow is the best way. If you look at a rainbow, you see these bands. You don't see a continuum, and that's not because of some designer.
Yeah. And you see a lot of, on these grids, you see a lot of blue-green. It turns out the blue-green space is pretty big, whereas red, like what we see as red, picks out a pretty small perceptual space. But yeah, that's basically the experiment, is to then ask people, what color is this chip? What color is this chip? And then you can measure, basically using like kind of simple information theoretic terms, the entropy over chip colors. And then you can measure basically given a set of color words in a language and the way that they're used. If I say a word, how much information am I getting about what chip is being discussed?
So you have a collection of chips which are essentially uniformly distributed in Munsell color space. So let's say you have 100 chips and they're equally spaced somehow in this color space. And now you're asking for what would it mean? And then you're trying to define how close can you get to saying a particular chip. I don't understand how this works quite. I mean,
if we were in a language where there was exactly one chip which was called red, and everyone agreed that chip was red, and no one called any other chips red,
Mm-hmm.
that would be highly informative for that particular chip. But we have
Right.
to average over all the chips. And if all the chips were like that, we'd have a system which was very informative, but also very complex because we'd have, you know, a huge number of color words to learn.
But so the question you're trying to, the goal, the task is effectively home in as close as possible on chip number 13 or something. Can you get, you know, if all the chips are numbered, so to speak, with
Yep.
these color words that you have, how much can you home in on the fact that you have chip 13 or something? Is that right?
Exactly. Yep, that's right.
And so then what's the conclusion of the study?
The conclusion is that you get an optimal trade-off across languages. So languages which have more color terms and more complexity in the system that they've learned get the benefit, right? You could imagine learning more color terms, but not actually having the space or the color system more efficient.
So,
and if you plot informativity versus complexity, the real languages fall along a kind of Pareto-optimal frontier. And like a bunch of simulated systems you could make up just by, you know, simulating, let's assume these are the color words and this is how they're distributed, all look much worse than what real languages look like.
wait a minute. Why don't you just take that space and you know, chop it up into equal boxes? What does that do? Is that not, does that fail for some reason?
If you chop it up into equal boxes, I mean, that's a good question. I think
so in other words, each one would have the same number of chips in it. Each bucket would have the same number of chips.
Yep.
It might not be physiologically possible to distinguish those chips correctly.
Think of the question in terms of the rainbow. You could take the rainbow and chop it up into pieces on the basis of the physical parameters or on the basis of the psychophysical ones. It's not the same pieces. That's the point.
Yeah. It turns out also that there's an asymmetry between warm and cool colors, which is something. So warm colors, it turns out, we have a hypothesis in this paper that they tend to be more in the foreground. And tend to be like objects and things we care about are often warm colors, and blues and greens are, you know, sky and grass and background kinds of things. And so it's actually the kind of space picked out by red and yellow and orange is very small compared to the blue-green space.
So the question there, I don't remember what the acceptor curves are, what the absorption curves are for the three kinds of photoreceptors, but there are two that are very close to each other, as I recall, and one that's much further away. Which one? I mean, in this claim that reds we care more about, would we not expect then that we would evolve a photoreceptor? Well, actually, two questions. One, why wouldn't we evolve a photoreceptor that does better at reds if it's not chemically impossible? Question one.
Yep.
Question two, I wonder what would happen to your experiment if you used a mantis shrimp. So mantis shrimps have like 15 color receptors or something. I don't know how they're distributed in the space in color space, but that will be a question of if you look at the mantis shrimp's color receptors, you know, any color receptor a mantis shrimp has, we presumably could have had in a first approximation. So if it has heavily distinguished, you know, it has a lot of fine distinction in the red color space. I mean, it also raises the question for us. An interesting corollary of what you're saying is, you know, we have 3 color receptors, cats and dogs have 2, mantis shrimps have 15, you know, various kinds of fishes have more. In your theory, can you explain why evolution has picked different numbers of color receptors for different critters?
I mean, I think the general theory would be kind of need, right? So there's some term here, which is like a need distribution over the colors we want to talk about, which I guess for mantis shrimp, I guess it would be talk about, but use and distinguish in their mantis shrimp lives. And so presumably that term would figure into it. I don't remember. It's a good question about, we had color vision collaborators on this paper who would know the answers about like the actual cones and
there's
those
an
people.
exact
You're
analog
right.
of this in phonology also.
What is it?
In phonemes.
Yeah. You mean what? But phonemes, I mean, we take a spectrogram, for example, and we can have lots of different forms in a spectrogram. And I mean, people have chosen to pick out, you know, 100 different things that they call, well, okay, so your point is, imagine that we can physically, with our throats, produce all kinds of different spectrogram patterns. One question I don't know the answer to, maybe you guys do, I'd be curious to know, if you imagine Well, it's a little complicated because by the time you've got an S, it's a big kind of mess in the spectrogram. And if you've got some definite vowel, it's much clearer. My question would be, to what extent are you filling the space of possible spectrograms with with the actual phonemes that get used? And to what extent, for example, well, I mean, another question like this is when you look at letters of the alphabet, and you put them in a feature space plot, B's and P's are very close together in typical feature space plots. How come we ended up using letters which are not readily distinguishable? Presumably, for phonemes, we want phonemes which are readily distinguishable in some way to our perceptual system. I'm curious, what do you guys know about this? I mean, for example, in the case of letter forms, that's a case where you can clearly see, I mean, it's surprising that so many confusingly similar letter forms survive. It's surprising to me, at least.
Okay, now you switch to letters. Let's go back to phonemes. There's an answer to the question, okay?
Yeah, please.
And in fact, Judith spoke about it in her talk. She said that babies are born with a certain number of selective feature detectors. They take let's say phone space, and they have selective detectors for some phones. But these selective detectors depend on whether you end up speaking a language that uses them. If you don't use them to make contrasts, and that's where these minimal pairs come in, then you lose them, or they become weaker, especially in second and third languages. So
yeah, I remember when my kids were young, there was lots of sort of things saying, play the kids the phonemes from all the languages of the world so that they will be used to these phonemes. I did try that. I don't think it had any effect.
It's not enough. They have to say them. Because
no, I realized that. I knew that even at that time. And that was but it's hard to even know whether they are saying them. If you're just a human who is not used to those phonemes, it's hard to tell if you're saying them. And in modern times, you can obviously get, a computer to look at the spectrogram and say, are you saying that thing that I can't tell whether, that I as a human can't tell you're saying? But to this question about so you're saying we are born with certain phonetic feature detectors. And
evolved ones, probably. They were
right.
Because we have articulatory systems that are capable of producing some sounds and not others. Birds are better.
Right. I mean, it's like the Huber Weasel experiment of the cats raised in an environment of vertical stripes, that if you don't use the horizontal stripes detectors, then those ones, then you lose those horizontal stripe detectors. And you're saying the same thing is true, the same kind of thing is true for phonetic detectors. So how many distinct, I mean, in the case of the primary visual cortex, we know something about what, at least of the things that we've recognized to look at, we know something about what feature detectors exist. In phonetic space, is there something known about the diversity of detectors that exist?
You can infer them. Being a vegan, I don't recommend chopping up animals to figure out what their sound detectors are. But you can infer what they are from their performance. That's why I said it was psychophysical. If they can tell certain distinctions apart better, then they probably have a feature detector for that.
What about other animals? What about a cat or a dog?
Yes,
Does it have?
It varies from species to species.
But
butterflies are different too.
Say it again. What?
Butterflies are different with colors too. So
right. But I mean, for example, for a dog, if a dog, started in some, country in Africa with some really funky collection of phonemes, and it learnt commands in that language and so on, it was used to that language. Then the dog is is moved to an English-speaking country, for example, and has a completely different set of phonemes. Does the dog have the same issue that a human has of not being able to recognize distinctions between phonemes? In other words, would you guess that a dog has the same intrinsic phoneme detectors that humans do?
Maybe it's born with the same ones, but there's another side of this coin. There's your innate feature detectors and your learned feature detectors. And the dogs that move. Okay, this story is sort of nice and a special interest to me, but it's not. Let's get back to the wider question here. and this is addressed to Ronnie, who has not been engaged so much in this yet. Tell me if it's a hallucination or confabulation on my part that Chomsky had one interpretation of the function, if you like, of universal grammar, which was that it distinguishes the kinds of utterances that express thinkable thoughts, thoughts that you can think, and you can translate this into something that makes sense, from those that are combinations, but that are not thinkable. Those that are UG compliant are thinkable. Those that are not UG compliant are not thinkable. And we're talking about a microcosm of that in the special case of, for example, mathematics. But tell me if it's apocryphal or true.
That's not my understanding of anything that Chomsky said about universal grammar. My understanding of it, and the details have changed, but the basic conception, I think, has always stayed the same, is that universal grammar is simply the name for the innate programming language that we have. So we have a computational ability as part of our linguistic ability, and part of our knowledge ends up being acquired, and it looks like what we can acquire doesn't change at all between humans. So we're all born with basically the same ability, and so that ability that is something that we can talk of as a shared programming language, which we're born with, and then we can, of course, argue about the details, and that's the point where different versions of the theory of Chomsky's and others, so different versions can look very, very different, but the basic idea is always the same, and that is that there is something that we're born with, some programming language. Into that we acquire a language, and of course there can be different ideas about how we acquire it, and that is UG. The universal here is because we all seem to be born with the same programming language, whatever it may be, and that's it. And calling it a grammar is a bit of a misnomer, and it's really a programming language. The grammars are the programs that we acquire.
Kyle, do you agree? I think.
Well, okay, there's an operational version of what you're saying, which I think is kind of interesting, which is, imagine you have LLMs with different, very different architectures. Is it the case that, in other words, can this statement about there is a universal grammar, there is something universal between humans, and you can learn this language, you can learn that language. Question would be, if you, for LLMs, different LLMs can learn the same things. There's a question of, are there things that an LLM cannot learn? Are there things that are, and likewise, for humans, for example, humans can't run code in their brains. Humans basically, I don't think anybody can run a non-trivial program in their brain. Maybe there's some savant somewhere who's capable of doing that, but it is certainly at best an unbelievably rare trait. It's not something that brains normally do. And I mean, I guess, well, I mean, this question.
People have also shown LLMs are also not good at running code.
Indeed.
Compared to generating code.
Absolutely. No, I mean, one wouldn't expect them to be good at running code. If one could make an LLM that had a recurrent stuff inside that one could train, they might be better at running code. But as it is, a feed-forward network is, which just has an outer loop, is really not, it's great for cached things. It's bad for computed things. I mean, this question about thinkable thoughts, I suppose the linguistic philosophers would assert that, for it to be thinkable, it has to be linguistifiable, so to speak. And I wonder to what extent, I'm curious to what extent you guys think that, actually, that as, in other words, are there, and it relates to these questions about sort of mathematics that we haven't cared about and all these kinds of things? Because are there thinkable thoughts for which we do not yet have words? Right? Because that will be, for example, there's a thing that's out there in the computational universe. It is in principle thinkable. It has a set of, rules by which you can go from one thing to the next and so on. But yet it is not something that we have attached human concepts and words to. So, I mean, my guess is that, like the LLMs, for the LLMs, having a word is an important kind of hook that lets them have some grist, that lets them make progress. Without the word, it's like, as you say, they can't run code in their brains. They can't go multiple steps without having this anchor of now there's a word, which kind of would encourage the idea that the only sort of easily thinkable thoughts are ones that wrap around human language with words and so on. But I wonder what your view of that is.
I'm thinking about a related problem, also I noticed that in Stephen's talk and when he talked about irreducibility, if you talk to many people who work on theoretical deep learning, they will say, "Oh, I work on how can we understand deep learning or how can we understand language models," but I always wondering what do they mean by understanding a neural network. It sounds like the neural network has it computes a certain function with a lot of neurons, millions of parameters, but it looks like in order to reach a human understanding, it's like we have some simple language that can describe what they're doing, which might look implausible for me. I'm not sure if that's.
Well, what you're asking is there a natural science of LLMs? I mean, there are lots of things in the world that sort of happen in the world, and the achievement of natural science is to reduce the things that happen in the world to things about which we can have narratives that we can sort of, capture in our brains.
Then it kind of assumes the natural world is compressible. It has this low dimensional structure. But what if a network is just random? It's just
well, I profoundly think that the natural world is not compressible in that sense. I mean, this is one of the big things that's come out of a bunch of science we've done recently. The very fact that we humans sample only those parts of this thing we call the Rulliad, this kind of limitable possible computations, the fact that we sample only parts, we have this sampling that is based on us being computationally bounded, that fact is what gives us the laws of physics that we have. If we were built differently and we did not have that kind of limitation, we would conclude different things about the laws of physics.
Carl, go ahead.
So I mean, I think the point I was worth making there is that it's okay, go ahead.
Yeah, sorry, I have to be a brute like that to keep things going. Carl, go ahead.
I was saying that Steven just saying that the way we do scientific discovery is fundamentally shaped by some computational limit of our humans.
Yeah, I mean, I think that what would it be? So this is a big question for neuroscience or for linguistics. Can there be a theory of neuroscience? Can there be a theory of machine learning? Can there be a theory of linguistics? In other words, is it the case that, that we can have, when we think about neuroscience, for example, is it the case that we can have a level of description that is intermediate between, oh, here's the electrochemistry of a neuron, and this is the word we say? Is there an intervening description? And in fact, those pictures I was showing that I just generated a couple of days ago about machine learning kind of do not encourage that idea. That is, those pictures tend to suggest that the things that come out in machine learning are things where it just sort of happens to work. It isn't something where there is a narrative set of principles that we can kind of compress and say how it works. It's just, it happens to work. It's kind of and I think it's it's really not obvious whether there's you mentioned Chomsky. I had a discussion with him a few years ago in which this whole question about he was complaining that the things I was trying to do were not answering the questions of the science of linguistics. And I guess my statement was, I'm not trying to do science of linguistics. I'm just trying to build technology. And I then put back the challenge, do you believe there actually can be a science of linguistics? Or is it so mired in computational irreducibility that there can be no science of linguistics? But anyway, it seems like there are various hands
It'll be Ronnie in a second, but actually before, when I said Carl, I was saying Karl, although I'm very happy to hear Caillou. Carl, say what you were going to say, and then we'll go to Ronnie.
Yeah, it must be very difficult with Carl's, K's, and Kyle's to manage. I was just going to submit, is the natural science of large language models itself neuroscience? It strikes me that the questions that people are posing about large language models are exactly what I pose in my day job, trying to, using things like brain imaging and the like. And if that is the case, then to understand a large language model is just the same as me understanding you. And how do I do that? I just do that by talking to you. There is no other way, I think. And I think that
you're denying the possibility of a sort of true sort of underlying science of neuroscience. I don't know. I mean, I think, but you're right. For example, I've done experiments. I'm surprised more people haven't done these. I've done kind of lesion experiments on image generation systems, for example. It's kind of cool. You zap pieces of the neural net and you see what happens to the images it produces. It's kind of like, what is the alien mind of the neural net that started off as a humanized mind, but then you make it alien by zapping pieces of it. And it's really quite remarkable what you get. I mean, you get these bizarrely non-human images. And, I don't know what, and actually there's really cool, I mean, you can get like, whatever it's called, hemispherical neglect, the thing that happens in, stroke patients and so on. You get analogs of that in these image generation networks.
It's fortuitous you say that, because that's a nice entree into a question for Kyle, because I read Kyle's presentation as identifying some of the very basic principles that we use in psychology and psychophysics, the principle of pure insertion, for example, Donda's subtraction methods, two alternative false
what are those? Just for my education, what are those?
I'm not sure. Carl can answer them. He'll know what I'm talking about. And just standard tools in neuroscience, or cognitive neuroscience at least, or cognitive science. And I was just wondering, has anybody, and Kyle, do you want to then take it to the next level, which would be either doing brain imaging on large language models or neuropsychology, which is exactly what Stephen was talking about, selectively lesioning an attention head, or 3 attention heads, or 4 attention heads, and seeing and using the lesion deficit model to start to get at the functional architecture in exactly the same way that we do in neuropsychology. So it's fortuitous that Stephen actually was sent, he's been doing that. That's exactly what we do in cognitive neuroscience when talking to neuropsychologists, after you've grounded things in the psychophysics and the psychology, and then you move on to brain imaging, which suggests that and of course the wonderful opportunity with large language models, you can do invasive electrophysiology. You can stick your needles in to different parts of the architecture and start to explore the principles of functional specialization and integration, and probably get to the same level of understanding that people in cognitive neuroscience are wrestling with at the present time, but now in a synthetic or a silicon context, and using the power and the beauty of large language models to endorse that test bed, that sort of digital twins of us, with a kind of validity that makes that exercise, I think, a very useful one to consider.
That's a picture, by the way, if you're interested. That's an image generation network, and that's showing what you get as a cat in a party hat if you zero, I think you're zeroing out here, particular parts of the network. So you see there, I mean, I'm curious, from a neuroscientist point of view, what do you make of something like this? I mean, in other words, you can, this layer, how would you describe this? What on earth is going on? I mean, this layer here, you change that, you get a bunch of random pixels. Here, you're getting, I don't know what you're getting here. I mean, how would you, this seems like it's relevant to what you're talking about.
Yeah, no, absolutely. And one example would be, are we looking at a disruption of the phonology? Are we looking at a disruption of the lexical representation, the semantic representation, the narratives? So at different levels, can we associate now the scale of the disruption induced by a particular lesion with the spatial location in the network itself? And that would be one way of, if you like, taking the principle of functional specialization in the neurosciences and applying it now to these kinds of networks. But it would depend upon you having some sort of coordinate system to make sense of this part of the network has a unique relation to the other part of the network. But of course it will, because the whole point of these networks is all about the relationships. It's all about the, as you've emphasized, Stephen, in it's all about the graph. So there is an architecture there, and then you're just looking for the morphisms between where you are in that architecture and the representational aspects that you're disrupting when you apply your lesions.
By the way, I think this is a picture, if I remember correctly. These are sequences where you're progressively reducing the weights, all weights, just reducing their values. It's kind of like you're drugging the neural net. And I don't know what you're giving it. I don't know what drug does that to humans. I'm sure you guys know what does that. But
psychedelics, 5-HT2A agonists.
You think will reduce the weights? Because the other thing you can do is increase the weights. And I think this one, it kind of blows its mind. It kind of increases. This is increasing the weights, and it kind of it goes blows its mind more or less. It's kind of, I don't know how to interpret these things, but this is what I think it's in. The image case, I think, is actually easier to handle than the linguistic case, because I think it's more obvious, when you see a weird image like this, if I gave you a pile of random words, you would make nothing of it. But these images, we kind of, I think, are a little bit more able, with our perception, we're a little bit more able to say something about them, more so than we could a pile of random words.
Okay, now KARL addressed a question to KYLE, whereas KATZIR had raised his hand. Do you wish to continue the question to KYLE, KARL?
If
you would like to answer it, yeah, I think Carl, you got the question. Are you going to
yeah,
use?
Sure. Yeah. Yeah, I think the brief answer is yes. I'm really excited about methods like that. This conversation just reminded me of the AI company Anthropic a week or two ago released a model that identified this part of the network in their model Claude that seemed to be responsible for the Golden Gate Bridge, and they kind of churned it up and released this chatbot, which no matter what you ask it about would kind of respond to you, but also just kind of start talking about the Golden Gate Bridge and relate everything it was saying to the Golden Gate Bridge. And it was a nice demonstration of exactly this kind of intervention. But yeah, for the kinds of linguistic questions I was looking at today, it was very much a behavioral intervention method. So, mess with the training corpus, train a model, see what it does. I think you're exactly right. The next step with that is, can we actually look mechanistically within the network? And there's all kinds of work like within linguistics in this space. So Chris Potts and his students at Stanford with Atticus Geiger are doing really interesting work like on exactly that, like kind of causal abstraction work. And there's a bunch of other interesting work in that space. So yeah, I think there's going to be a lot of interesting stuff there.
What is your intuition of how far you can go with those kinds of things? I mean, neuroscience has proved really difficult to make these higher level statements. We can now make more accurate probes in neural nets. Does that feel to you like, oh, well, first of all, do you think there's going to be a grand theory? Question one. And how much does it help you to have more data, more internal data rather than just behavioral data, so to speak?
Yeah, I guess I'm dubious there would be a grand theory, but I think we'll figure a lot out. And I suspect we're gonna keep finding a lot of these like abstractions and representations that we know and love from and their work and linguistic theory and psycholinguistics. Like I suspect we're gonna find a lot of that there, and it's not gonna look neat and tidy and exactly the same as it was in our theories, but like those kinds of things are gonna be there kind of because we think they have to be there. So things like hierarchical structure and for subject-verb agreement, um, like we don't something that looks kind of like that, you can find representations of, and I don't think we're gonna like some perfect trees are gonna pop up, but I think something.
If it's short, say it. If not, Ronnie has been waiting a long time. Go ahead, Eva.
Oh, yeah, I was short. I was going to say to that point that I don't think it's that easy all the time. The Golden Gate Bridge example is a really nice one of a case where you can sort of find a part of the network, but because these networks are so interconnected, a lot of information is often kind of just so dispersed across the network that it's very difficult to actually identify something through these types of like model ablations. And I think that's also going to be true for a lot of these types of abstractions that we think are interesting and may be very difficult for us to identify them that way, which is why most work tends to be this other sort of behavioral approach, because it's so scary to try to figure out what, all of these connections could be.
The point made, Ronnie.
So I had one general methodological question to Stephen, and that's regarding what I understood as the general pessimism about the computational reducibility of things, and I wanted to ask you how do what looked like scientific discoveries over the millennia fit into that view? So if things are irreducible, so why does it look like there is so much reducibility with probably plenty of stuff that we can't understand and can't have shortcuts for, but there are those chunks that were discovered, and so how do they fit in?
Right, good question.
Then I had another question but
okay, so to address that, because it's really interesting. I mean, the answer I think is interesting. One of the things you can theoretically establish is that within any computationally irreducible system, there will be an infinite number of pockets of reducibility. In other words, when there is this thing, which in general we say you can't predict everything, there will always be these particular things that you can predict. You can say of the Rule 30 pattern, it will always have, the edge will always look like this. You can't say everything about it, but you can say some things about it. So then science has consisted of finding these pockets of reducibility. In fact, our very existence, it could be the case that nothing about the world was in any way predictable. It would be hard for us to be organisms of the kind we are if nothing was predictable. I think if I've understood Carl's theory of things, Carl has sort of made a point of the fact that, we set things up and we're built so that we can live in these predictable parts of the world, so to speak. And so what science, I think, is the finding of more and more pockets of reducibility. And the fact that there are an infinite number of pockets of reducibility tells us that science will never be over, every invention won't have been made, etc. The question of whether the pockets of reducibility that we find are ones we care about is a different question. And that relates to Caillou's point about, when a theorem's interesting and so on. Yes, there is a theorem that jumps from here to there, but we may not care about that. It's a piece of reducibility we may not care about. But yes, the existence of, in a sense, computational irreducibility is the proof that science will never end. Because there are these... Go ahead.
Just a quick follow-up then. In that case, is there a reason to be more pessimistic about there being interesting pockets of reducibility in cognitive science than there are in the structure of materials or anything else?
Oh, that's a super good question. I think we have no idea. I mean, the fact is, okay, so in natural science, the pockets of reducibility are kind of where we live and where we build technology. There are certain aspects of natural science, like, for example, let's take fluid flow. Smooth fluid flow, we have pretty good theories of. We use those theories in designing lots of kinds of things. Turbulent fluid flow, on the other hand, we don't have such good theories of, and we don't tend to use it in technology. We kind of have to avoid it. We have to do things around it. So in other words, in in terms of our experience of the world, when we do technology, we're doing that within pockets of reducibility that we found. And so, like for example, here's an example. What is physics? Physics tends to be the study of things we can say about certain aspects of what the natural world does. There are areas, like even fluid turbulence, that are rarely talked about in physics because there's very little that the methods of physics can say about it. So, I think so now you ask the question, let's compare physics and cognitive science. Which one has more pockets of reducibility? And one of the things I suppose about physics is there are parts of physics that will not have computational reducibility, but which we choose not to interact with in our life in the world, in technology, and so on. In cognitive science, are we having our noses rubbed in the computational irreducibility because the things we need to know about are ones that have computational irreducibility? I mean, another good example of that is in economics, where it's the same question. There may be things that we can establish about economic systems, or we can have a general law like general relativity or something about economic systems, but it may be about an aspect of economic systems that we don't, as humans right now, care about. Some weird thing about the details of velocity of money in different situations that isn't telling us, should we buy or sell the stock kind of thing. So it could be that in cognitive science as well, that there may be theories, there may be grand theories that can be had, but they're about things like, I don't know, to make it up, some weird correlation between neurons in this place and that place and so on. And it's like, that's amusing, but we don't care. Or for example, a good example is EEG. It might be the case that, we can have some theory that tells us about why, brain rhythms are the way they are. But so far as I know, there's not a lot of connection between those brain rhythms and, well, there's some connections, but there's not detailed connections between those brain rhythms and a bunch of detailed cognitive behavior. So, I mean, in other words, we could have a theory of EEG. We could be very proud of that. That's a slice of reducibility, but it doesn't tell us about the things we're really interested in cognitive science. So I think that's but it's a very interesting question. Are there, what's the density of pockets of reducibility? And are those pockets aligned with things that we care about in that field?
Thank you. That makes a lot of sense. Yeah.
Thanks. It sounded like you had some other comment or something. Yeah.
Yes, but I don't know how much time we still have.
We have 3 more minutes. 3 minutes.
Okay. Yeah. So maybe not enough for what I wanted to ask.
Theorem, so.
Yeah. So maybe just a quick follow-up on what you just said. So I think the view from within linguistics has been starting from Chomsky's early work, but continuing that there are some interesting pockets of reducibility, not stated in these terms exactly, but I think something that can be understood like that around certain things, like certain properties of what can be seen as a programming language that we're born with. So, and certain other things, and then there are lots of other things for which maybe there is no good theory and that are left without analysis. And so I think the way that traditional or that theoretical linguistics traditionally partitions the things into what is considered interesting and what we would have perhaps wanted to like to understand, but we can't. Maybe there is no theory of that, and it's treated as some kind of noise, even if it's not really in. I think that fits the kind of way that you were talking about pockets of reducibility, I think very, very nicely. So yeah, I like that perspective.
Yeah, no, I mean, look, for linguistics, it is really, I mean, I'm very curious what pockets of reducibility there are. And I know there's been lots of controversy in linguistics about, what's universal, what's not, and so on. And Yeah, I mean, and by the way, with respect to LLMs, it is kind of disappointing that all you can do right now, typically with them, is ask them questions about what they think about things. In other words, we're not, it's disappointing. I mean, like, for example, I'll give you an example of one might not be obvious. We build software that in some cases now uses LLMs, and we need to do software testing. And the question is, we're trying to do regression testing. Are the results that we get now the same as the results we were getting before? So how do you do that with LLMs? The only way we found to do it is to ask the LLM. So in other words, you ask another LLM, you say, given this output that has now come out, is it the same? Is it semantically the same as the output you got before? The only thing we found to do there is basically ask an LLM to make that decision for us, which is kind of a, I don't know. I find this rather unsatisfactory, but it's a, and it's kind of LLMs all the way down, because eventually, the LLM might be uncertain, then you have to ask another LLM, how certain was that LLM, and so on. And eventually you just say, it's probably good enough, and you release the software or whatever.
Okay, with that, I think we can call this meeting over. I have to rush back to be able to upload them all so that everyone can see this, even the panel. I'll try to get up before the end of the day. There were very good comments in the comment section, but we never got to them. And what I recommend to attendees is that if your comment really is urgent and important, please raise your hand. Don't just put it there, because otherwise it relies on luck to get to it. I want to thank all of the participants and encourage you to come next week, because it's not over till it's over.
Nice to meet you all.
Okay.
Bye.
Bye-bye.
Yeah.